So in 5b, we want to show for the total claim amount process S in the Cramer Lundberg model that S has independent increments. Basically what we're kind of doing in entire exercise 5 is showing that when we're looking at the Cramer Lundberg model, the characteristics of the total claim amount process S is not that different from the characteristics of the total claim number process N. Because what did we show in 5a? Well, in 5a, we showed that S is a stationary process, meaning that for times S smaller than t, the increment in total claim amount from time S to t has the same distribution as the increment in total claim amount from time 0 to t minus 1, meaning that as long as the time interval we're looking at has a fixed length, then the total claim amount will have the same distribution over that interval, no matter if we're looking at that interval in the beginning of time or somewhere further along the time axis. And that is also a characteristic of the homogeneous Poisson process, which drives the claim number process beneath the Cramer Lundberg model. So in 5b, we want to show that S has independent increments. The exact thing that we want to show is actually formulated in the book, so I'll just not write that down. But essentially, it's enough if we can show so what we want to show is for some time points, t1 strictly smaller than t2, strictly smaller or smaller than equal to t3, and strictly smaller than t4, with 0 being down here. What we want to show is, well, I guess t1 can be 0, so we'll just do this instead. What we want to show is that we want to show that the increment from time t1 to t2 in total claim amount is independent from the increment from time t3 to t4 in total claim amount. Now this is pretty hard because we don't really know that much about the distribution as such of S, right? It can be pretty tricky to show this using just distribution functions. So the thing we're going to do is we're going to borrow a trick from the realm of characteristic functions. So what you will learn later on in Advanced Probability Theory 1, or the course Stock 2, is that two stochastic variables x and y are independent if and only if their joint characteristic function is equal to the product of each of their characteristic functions. And to write that down formally, we want to write, so if and only if their joint characteristic function, which is the mean value of e to the I, and then x1 multiplied by x plus x2 multiplied by y. So this is how we write down the joint characteristic function of two stochastic variables. So if I wanted to write down the joint characteristic function of three stochastic variables, I would have added x3 multiplied by z inside here, or something like that. So this is the characteristic function of the joint distribution of x and y, and we want to show that this is equal to the product of the characteristic function of x multiplied, so the product of the characteristic function of x and the characteristic function of y. So this is what we're going to show. So I'll just write here, i.e. show that the mean value of e to the I x1, and then increment from time t1 to t2, multiplied by e to the I x2, and then increment from time t3 to t4. So I've just written down the relevant version of this side of the equation for us. So this is the characteristic function of the joint distribution of the two total claim amount increments. So we want to show that this is equal to the product of the characteristic function of S of T1 to T2 and the characteristic function of S of T3 to T4. Looks like I'm missing a T up here. T3 to T4. Okay, so now I've written down what it is I want to show, right? And just to make it very, very clear, I'm going to put an orange box around it. This is what I want to show. And the strategy will be that we'll start by calculating this side. So we'll start by calculating the joint characteristic function, or what we call the characteristic function of the joint distribution. And why will this actually not be too hard to show, this equation? Well, the thing is, we've already done a lot of the hard work in 5a already, in the sense that we do know what the characteristic function of the increments are given as. So essentially what we know from 5a also, so 5a, what we showed there was that for any time point s to t, with time points s and t, so where s is strictly smaller than t, well then the characteristic function of the increment in total claim amount is given by the following expression. It is given by the sum over the probabilities that n, so the increment in claim amount from s to t, the probability that is equal to k, for k ranging from 0 to infinity. And then for each outcome we multiply by the expected value of, so essentially we multiply by the characteristic function of the claim size to the k. So this is an expression for the characteristic function of the increment in total claim amount. And we also found a closed expression using the Taylor series for an exponential function. So we actually concluded that we have a closed expression for it, as I have written up here. And this is really just incredibly nice, because this means that we've done most of the hard work for the right-hand side of the things that we want to show. So we just want to show that our left-hand side looks something like a product of the two of these things here for the relevant T1, T2, T3, and T4. So that is what we'll do in the next video, where we will get started with the calculations.